So good morning, everyone. This is the Wednesday session, so we're midway through the week. The first talk today is by Tom Russell. He'll be talking about the accretion, ejection, coupling, and outbursting X-ray binaries. Tom, you can take it away.
Thanks, Picky. I'll just share my screen. Hang on a sec, sorry.
Just some housekeeping. I'll be reminding you of the time left, maybe at 5 minutes.
Okay, cool. Thanks very much. Yeah. All right. Good morning, everyone, or I guess afternoon or night or some terrible time, depending on wherever you are. For those of you that don't know me, my name's Tom Russell, and I'm a postdoc at INAF Palermo. Firstly, I want to thank the organisers for putting all of this together. It's been a really great conference, and so far there's been some really fantastic discussion. So we've already had quite a lot of discussion about the accretion-ejection coupling in X-ray binaries. We've had quite a few talks over the last couple of days, but today this morning, I'm going to basically be focusing on the coupling around state transitions. So in particular, looking at the jets and how they evolve as the source transitions between the hard and the soft states. I do want to note that I'll mostly be discussing this evolution based around observations of black hole X-ray binaries, mostly due to them typically having better observational constraints, but I will do my best to make the connection to neutron star systems as well. Okay, so you're very well versed in X-ray binaries, so no need for a big introduction, but I will briefly introduce a few key points. So broadly speaking, two types of jets are observed from these systems. We see a steady compact jet during the hard state, so over here on the left, and a transient jet that's launched around and then a transient jet on the right here that's launched around the transition from the hard to soft state. That compact jet or both of which were discussed in some detail over the last couple of days, but the compact jet has a flat radio spectrum and has velocities typically assumed to be mildly relativistic, although see Alex's talk from yesterday. And then the transient jet, on the other hand, exhibits a steep radio spectrum, which originates from ejected optically thin synchrotron emitting plasma that's shot out from the system and collides with either the pre-existing and slower moving jet or with the surrounding environment, which again was discussed yesterday. And these ejecta can be observed to be superluminal, traveling at apparent velocities greater than the speed of light. But some have also seemed to be mildly relativistic as well. Now, to show a broad overview of the evolution of these jets around the transitions, here I show the radio and X-ray light curves of the black hole system, MaxiJ 1348, which was some great work, recent work led by Francesco Caritanuto. Now, I notice I've been told that the small portion of the slide is cut off at the bottom. So just the x-axis here is time, and this extends over about 120 days in total. So what you see is during the early hard state, we see the X-rays rise up the top. So we've got X-ray light curve, hardness ratio, radio flux density, and then the radio spectral index. So during the early hard state, we see the X-rays rise. At the same time, we see a steady compact jet exhibited, and you can see this is characterized by that flat to inverted radio spectrum. Then as the source transitions from the hard to soft state, that compact jet is quenched really quite dramatically, and then that transient jet is launched. And that transient jet is characterized by bright radio flares that you can see here. And you can also see that the emission transitions from optically thick to optically thin synchrotron emission. Then during the full soft state of the outburst, we don't see any jet emission from the system, although as shown by Francesco's work here, we may see some residual radio emission that's due to those ejected knots that are now disconnected from the system, propagating and have propagated out, and they're interacting with the surroundings. Then as the source transitions back to the hard state from the soft state, we see that steady compact jet re-establish itself. Now, while we have a decent phenomenological understanding of this evolution, and we can see it in play, in real time, at present, we don't understand precisely what is happening and when, or how long each of these things, or how long each of these steps take. And we certainly don't understand the causal connection between the causal connection with the accretion flow. So in this talk, I'm going to outline what we currently understand and have observed, with a particular focus on a number of recent outbursts of these systems. So breaking this talk up into sections, first I'm going to discuss what we think might be happening that causes the quenching of the compact jet. So showing a schematic of the broadband SED of a black hole X-ray binary in a typical hard state. So this is flux density versus frequency, and I also show the approximate observing bands in the bottom there. So we see a flat radio spectrum, which is we see a flat radio spectrum, which is basically just the superposition of single synchrotron spectra from different distances along the jet, where the higher the frequency probes closer to the black hole. So basically our highest energy synchrotron spectra is the most compact region in the black hole where the particle acceleration occurs, and its frequency scales inversely proportional with the distance from the black hole. And then this flat spectrum extends up into the infrared band before it breaks, and this location of this jet break indicates that most compact region in the black hole, that most compact region in the jet where particles are first accelerated. We also show the disk emission and the power law emission there. Then as that source softens, what we think happens is basically that jet break, the highest energy jet emission quenches, disappears, it switches off. And we see that jet break shift to lower frequencies as we lose those higher energy synchrotron spectra. The red dots there indicate what we'd see from the radio spectrum. So we see two radio points there. We see a flat spectrum, then we see a steep spectrum. And then as the source enters the soft state, the jet has either, the particle acceleration region has presumably moved all the way below the radio band, and we don't see any radio emission anymore from the compact jet. Now we clearly see this evolution in real data, and here's some of Rob's early work on GX339-4, which shows the radio light curves, the hard X-rays, and the soft X-rays, and we clearly see that the radio emission fades away just as a source transitions from the hard to soft state around the same time as the hard state, as the hard emission just fades away, just dramatically decreases. Now, also, I'll talk about this a little bit more in a minute, but we see that we see the compact jet recover after the soft to hard transition at the end as well. Now, this seems to happen in this monitoring. It seems to happen on the jet seems to be quenched on timescales of about a week. We can also see that evolution in the infrared and optical band, where we see the infrared and optical where it's been dominated by the jet emission fading quite rapidly on sort of timescales of 1 to 2 weeks, and this is indicative of that high energy jet emission quenching. And we were recently able to track the complete jet spectrum reasonably well for a compact jet. This was done using multi-wavelength observations of the black hole X-ray binary MaxJ 1535-571. Now, like the schematics I showed previously, here we're showing the flux density versus frequency, and we see the same evolution depicted in those schematics, where initially the jet spectrum extended all the way up to the infrared band in September 12 to 16, and then then the jet emission changed remarkably, and that jet break evolved rapidly down into the radio band by September 17, and then below it by September 21. And now this evolution appeared to occur as the source transitioned from the hard intermediate to the soft intermediate states. Now this occurred on timescales of less than about a day, which is very rapid for this. But those rapid timescales also match some previous work by Alexander van der Oost and Poshak Gandhi, where they were able to construct
Is it just Tom, or have we lost everyone in Zoom?
I think we lost Tom.
Okay. Okay. So
Yeah,
it's not
apparently
us,
it's
it's not
okay
us.
here.
It works. I thought it was me, but no.
Yeah, maybe his connection had a problem.
Oh,
Oh,
he's
he's
back.
back.
Tom, you're back.
Yeah, I don't know what, are you there?
All right. Do you want to just take it away from where you left off? Do you know where
Yeah.
you left off?
Well, it's where Zoom disappeared, I
Oh,
assume.
good.
I think I got to this point, right?
I think the next slide, if I'm not mistaken.
No, I never got to the next slide, so it must be.
Oh no, you were
Um,
far up. It was, yeah. The
I got to this
Maxi J
slide, right?
1537 was done.
Yeah, okay, then I got to this
Yeah.
slide. So then, sorry about that, everyone. Then in the soft to hard state transition, that compact jet relaunches. And what we actually think is happening is we think that basically the same thing is happening, but in reverse. But basically the same thing is happening in reverse, where that jet spectral break shifts from low frequencies to high frequencies as the source softens, as the source re-hardens. Now, we've actually been able to observe that occurring, both with a change in the radio spectrum down in this bottom left here, by some work by Stefan Corbel, and in the top left, also some work by Stefan, where you could see the infrared and the optical recover over the timescales of sort of like a few weeks. But we're also able to track, which also match really well with some work by James Miller-Jones and Emrah Kalemsi, showing the same thing where the lower energy jet emission, the lower frequency jet emission recovers first, followed by the higher energy, the millimeter and then infrared, over the space of a few weeks. And we're also able to track that with multi-wavelength observations of the black hole X-ray binary Maxi J 1836-194, where again, the broadband SED show that jet spectrum initially in the intermediate states, not extending up into the infrared band. And then as the source hardened further towards the hard state, that jet spectral break shifted up to higher frequencies. Now, unfortunately, we haven't been able to make any direct connection to the accretion of the jet quenching and recovery with any specific properties of the accretion flow. Tentatively, there seems to be some connection with the location of the jet spectral break to source hardness and possibly X-ray photon index, which was shown with some really impressive work by Kari Kolonen, who analysed the location of the jet spectral break in both black hole X-ray binaries and some AGN, showing some sort of a phenomenological connection. However, to date, there's only been a couple of systems that have a time-resolved evolution of this jet break. Almost all of these points here are static. So we need more sources to determine precisely what is driving those changes. And if the source hardness is connected with the changes in the jet, what is driving those changes in the source hardness as well. Now for neutron stars, in terms of compact jet quenching, the picture is even less clear. Some sources we think show jet quenching, some don't. You know, for example, here's some images. Here's some results from Simone Milari in 2004, where they detected soft radio emission in the soft state from 4U1820-30 and SIR-X1. Whereas then conversely, for example, Nina Gazinski with 1RXJ1804 detected strong radio quenching as the source transition from the hard to soft state. And we see that here where the radio emission is detected quite bright, starts to fade, and then is not detected following the source transitioning to the soft state. Now, however, recently some really great work by Maria Diaz-Trigo showed that the radio to millimeter spectrum from the jet from Aquila X1 evolved in such a way that was entirely consistent with what we think we are seeing for black hole jet quenching and relaunching. So we see a radio to millimeter spectrum that's relatively flat with a jet spectral break either in or above the millimeter band. Then as the source sort of moves towards a soft state, that jet break must move below the radio band and becomes optically thin, the jet spectrum. Then as the source recovers at the end of an outburst, as the source starts to fade away at the end of the outburst, that radio spectrum then begins to flatten again and extend up, and the jet spectral break extends up into the millimeter or above band again. Now, interestingly, Maria was also able to make some tentative connection between the evolution of the jet spectral break and the X-ray hardness in line with the results from other systems, such as like Nina's work, where that jet quenching seems to be related to lower hardness ratios. So it does appear that if a neutron star does have jet quenching, when it does occur, it could be occurring in much the same way as in neutron stars it does for black holes. So now I'm going to move on to the transient jet launching. Now, as I mentioned previously, we detect the transient jet, the emission we detect from the transient jet is optically thin emission from an expanding knot of synchrotron emitting plasma that's been ejected from the system. In the radio band, we see a steep radio spectrum which flares as it interacts with the surroundings. So you can see that here in the same schematic that I'm showing before. We see a synchrotron emitting blob that's moving, that's been ejected and disconnected from the black hole. And as this sort of moves out, collides, interacts with the surroundings, it flares, and we see a steep radio spectrum from that.
Actually, there's a problem with the slide we have here in the room and the one on Zoom.
Bob,
Yeah.
we are hearing you and very loud.
Okay, now it's okay. We have the same slide, but there was a delay. No, I mean, it's still very strange. We do not see the same slide. Okay, now it's the same. Okay, sorry for that.
Tom, sorry.
That's okay. It's so now showing some real data of one of these events. So what we can see is this is again pointing back some work by Francesco.
I think we have, no, it's okay now. Yep, sorry.
I think there just might be, is there a delay between the slides, is there?
Are you changing slides or are we just seeing?
No, I'm just sitting at the optically thin radio flares.
Okay.
Okay.
Yeah.
Looking at some real-time data of this, you can see this with going back to Francesco's work. You can see that we have that optically thick jet spectrum from the compact jet, which then transitions to the steep spectrum transient jet. And you can see that as there's quite a bit of radio flaring going on. And this is, the reason for this was basically the launching of the relativistically moving jet knot that was observed to propagate out and away from this system. So in this image, we're looking at jet knots that are propagating out and away. The magenta plus sign is the core source position. And then the first jet knot that was launched is marked by this red cross, which moves out in time. So time goes left to right, top to bottom. And then there's even a second jet knot, this blue cross, which moves out as well over time. So now I'm going to focus the next few slides on the 2018 outburst of Maxi J 1820 plus 070, where I'm really mostly going to be discussing some fantastic work led by Joe Bright, Matilda Espinas, Jeroen Homan, and Callum Wood in particular. And as you can see from the light curve here, the radio light curve on the left from Joe's paper, you can see some nice bright radio flaring around the time that just after the jet was ejected. And on the right-hand side, you can see some really nice, a really nice selection of images where you can see those jet knots sort of propagating out and away from the system over time, and they're moving very rapidly.
It's okay, you can take some extra minutes.
Okay, so now Jeroen Homan did a really great analysis of the radio light curves and the X-ray emission from this source, and finding that the radio flare started right around the time that the X-ray emission showed some really dramatic changes. So on the left, we're seeing the X-ray light curves. We see some X-ray brightening across all bands, and we see the power density spectrum down in the bottom change from the type C to the type B QPO. Now, analyzing the radio light curves, we see the flaring start right around the time that red line is, and that on the left-hand side, that is marked by the red line as well. And you can see that that is entirely consistent with the onset of the presence of the type B QPO. Although which we've always been trying to connect, we've been trying to connect this, what's the causal thing in the accretion flow that produces the transition of the launching of that transient jet. Now, while we've got the radio flares connected really nicely, as Jeroen discusses in his paper and as Rob presented in great detail in 2009, the timing of the radio flare doesn't necessarily indicate the moment the ejecta are launched. There's an unexpected but unknown delay between the launching time and the radio flaring due to the ejecta time travel and the optical depth effects. So the best way to work out the true moment of ejection is, and to pinpoint that, and to pinpoint it to changes in the accretion flow, the best method is to track the motion of those knots as they move out. For Maxi J 1820, this was done extremely well, where the ejecta was detected in both radio, as we showed with Joe's Nature Astronomy paper, and in X-rays as well, as shown on up the top there with Matilda Espinas's work. This is a selection of Chandra images that she presented. And then fitting for the positions of those knots, you can then trace out the motion as I'm showing down in the bottom right, and extrapolate back in time to determine the moment of zero separation. Now, fitting for those positions, they found that these knots showed superluminal motions where the ejecta were traveling really close to the speed of light before decelerating significantly
5 minutes,
at
Tom.
late times as they presumably interacted with the surrounding environments. However, these knots were moving really fast. So for VLBA observations taken just a few hours after the ejection event, the rapid motion of the ejecta led to some issues because those jet knots were now smeared out over the course of the radio observation. And some really nice work by Callum Wood was able to correct for this smearing by using some really fine time beaming and a dynamical phase center tracking technique, which was able to better reconstruct the ejecta position and recover a previously undetected ejected knot. And you can see this on the figure on the left here, where the top image shows the uncorrected smeared image, where the knot is detected, where the knot is shown, the initial detected knot is shown as component A. There's the black hole is marked by this black cross here. There's a possible component E to the receding to the other side. But then after it's corrected, you can see that possible component E disappear. The position of A changes a bit, but a new component C is reconstructed further away from the black hole. So important thing to remember here is A is closer to the black hole, C is further away. But very interestingly, when you combine these results with those from Joel and Matilda's work, what you actually find is that the component A was launched first and was traveling much slower at around 0.3 C, while component C was launched later, but traveling at much higher velocities, around 0.97 C. And in fact, it was this later ejection C, which was responsible for those much larger scales that we were able to observe these knots propagate out to. Then comparing these launching times with the X-ray evolution. So here we're showing the work, the X-ray light curve and results from Jeroen Hoeman's work. And Callum's work shows, so the time that component A was launched is shown by these magenta vertical lines, and the component C, that more faster moving one, the ejection time of that is shown by these vertical green dashed lines. Now, from the size of the component A, which is quite large, as you saw from those previous images, you can work out that that actually took 6 hours to be launched out from the system, which is entirely consistent with the onset and the presence of this type B QPO, meaning that this is the first time that we've been able to really truly connect the presence of that type B QPO with the jet launching. However, interestingly, there was no similar connection detected for the more rapidly moving second component here, which is interesting in itself. So this is a really fantastic result and does show for the first time what appears to be a clear connection between the jet launching and the onset of the type B QPO. But as you can see, there's still some really interesting things going on. In particular, we've got knots launched at completely different velocities. We've got no significant changes in the X-rays around that second faster moving knot. And you can also see how hard this is to do. We need to take into a lot needs to be taken into account before you can finally make some of that connection. And in particular, maybe this picture isn't quite so clear for all other systems. The best other studies where this has been done, some work again by Francesco, some work by myself and some work by James Miller-Jones, all seem to suggest that the jets were launched a couple of days before the first onset of the type B QPO. However, all of these studies were hindered by either a lack of high spatial resolution radio observations very close to the launching event, which we saw previously can have a really big impact on the results with the two components being launched when we only thought one was launched, or high cadence X-ray observations, where in particular James's work here, the launching event coincided precisely with a couple of day gap a 4-day gap, I think, in the X-ray monitoring. Now, in terms of neutron star systems, the picture is even
Tom,
more.
a minute.
Yeah, I'll finish on time. It is even more complex, where the transient jet ejection can be observed from highly accreting Z sources, but the connection to X-rays isn't quite so clear, and there hasn't been any evidence for jet ejecta around state transitions. Taking a look at some results from SCOX-1, there's some really fantastic and extremely detailed work by Saramotta recently, which showed a tentative connection between the mildly relativistic jets that are observed to be launched around the transition between the horizontal and normal branch with an X-ray power spectrum showing a flat top noise. And there was also a potential connection between the unseen ultra-relativistic ejecta that are launched with the appearance of normal horizontal branch oscillations, which broadly correspond to type B and type C QPOs in black hole systems. So in summary, there's been a lot of recent progress showing that jet quenching and relaunching of compact jets, as well as the launching of transient jets, but we still lack a comprehensive understanding of the causal sequence of events leading up to these changes. Recently, for the first time, the type B QPO was able to be directly connected to the launching of the jet knot, but that picture still needs to be filled in somewhat, especially for other systems. And while we've got a better understanding of how the compact jet is launched and relaunched, is quenched and relaunched, we have yet to pin this down to any specific changes in the accretion flow. We're also yet to explore if there's any connection between the compact jet quenching and the transient jet launching, which seem to happen around the right time. So we've still got a lot of questions to answer, and we need we need more data on this. We need a lot of early time, high spatial resolution radio observations to track, coupled with high cadence X-ray observations to track the launching of the transient jet. And we need a lot of multi-wavelength observations to track the compact jet as it quenches and relaunches. All right, thanks very much.
Thanks, Tom. Let's start with questions in the room. I don't see any hands raised. There's nothing in Slack yet as well. Is there anybody in Zoom who would like to ask a question?
I actually myself had one. So this is going to be a bit of naive from X-ray observer. So when you talked about the knots having those very different velocities, so A and C, right? With the C being a lot faster. So why? Do we have any ideas? Or is it like just one of those big mysteries that we'll have to move to the discussion?
I think it's just one of those mysteries. Other people like Rob, he's got his hand up at the moment. He'll probably have a better idea than me, but we don't know, right? There haven't been that many where we've been able to really detect these close in, slow moving, and then fast moving jet knots. But then in neutron star systems, we see it with SCOX-1 with the stuff that Saramotta showed. So I don't know. I think it's a bit of a mystery.
Rob has also his hand up.
There's a question in the room, which I think, yeah, please go ahead.
Hi, Tom. Thank you for a nice review. In the previous microquasar meeting, I asked you about the possibility to study the variation of the break frequency at the beginning of an outburst. Has anything been done on that, or is it too difficult to organize all that at the beginning of an outburst?
Yeah, good question, Nick. And I do remember that we spoke about this. It's really hard to do. You basically need to be on source really quickly. So this is a question that Nick asked me many years ago, And this is not necessarily the part that I was showing in MaxiJ 1535, where we see the jet brake move from high to low frequencies. This is as the source rises in the hard state rise. And do you see the movement in the jet brake? I think, Nick, it's a bit too difficult at the moment. We just get lost in error bars. We need to have really great coverage through there to be able to pin it down so well. You know, our error bars are generally of order of magnitude size. So the motion that you're looking for, I don't think we can do with observations just yet. We need.
And we lost him again.
Let's give.
Somewhere in the infrared band, and we can see it clearly in the extruder band or something, that'd be great, but we haven't really gotten there yet.
Tom, we lost you there for a few seconds, I think. But maybe we can take this discussion on Slack, and thank Tom again for the great talk.